Okay, so I've introduced GlowScript before. No.
No.
No. Oh, okay. So this is GlowScript, and it's essentially like online VPython. Okay, so you don't have to install anything. What you do need is a browser that supports WebGL. So Chrome works. Firefox, I think, works. So there's a couple of browsers that work and a couple that don't. Definitely Chrome works. Okay, so you have to have that. And then you can log in with the Google ID, and then you can save your programs and you can run them wherever you want. That's pretty nice. You don't have to, the nice thing is you don't have to install anything. Okay, so let's create a new program, and I'll call this eField rod. Okay. Now, there in GlowScript, actually, there is you can actually write your program in JavaScript or other things, but if you have this top line up here, GlowScript 1.1 VPython, then it's loaded VPython. And it mostly works as VPython does. It doesn't 100% work the same. There are some things that are different. Okay? But most of your stuff that you would write in VPython would work here. You don't have to import anything. You don't have to import VPython. It's already imported. Okay, let's just make the simplest program. Let's just say this. So it has this sphere function built in. And if I write my code and run it, it automatically saves. And then I have my sphere. And of course, you can rotate it around. You can zoom in and out. It's a 3D thing that it takes care of the 3D part. We don't have to worry about that. You don't have to install anything. Okay. Some other objects that we have that you may use, that we'll use, in fact, arrow. Arrow is another function. Let me just run this. I'm not sure. Yeah. It just makes an arrow. But you can use that to represent the electric field or things like that. And at any point, if you're not sure what things do, if you click this help over here, you can say, oh, arrow, how does that work? It tells you down here. An arrow has a function, has a position. The shaft width right here is how wide that thing is. And the axis is a vector from the beginning here, the position, to the end right there. So you can describe all those things. So you don't have to remember anything either. So hide help and go back over here. Okay? Let's just, for simplicity, calculate the electric field due to a point charge. Okay, so I'm going to say K equals 9 times 10 to the 9th. That's that 1 over 4 pi epsilon naught. Q equals, let's say it's 1 nanocoulomb, so 1 times 10 to the, let's say 1 microcoulomb. 1 times 10 to the negative 6. So I'm going to go ahead and make my charge and say, let's just say, what should I call it? Let's call it a ball. And let's put it somewhere. Let's put it at position, making up stuff here, 0.01, 0.040, and give it a radius of 1 times 10 to the negative 3. And make it red. And let's just run it to make sure things are looking okay. There's my charge. Now, let's make RO. RO is the vector location where I want to calculate the electric field. So let's pick that at...
That's a cool question.
Yep.
Oh, okay, never mind.
No.
I see. Pause equals vec. That's just the position.
That's the position. Yeah, so if you go back over here to sphere, there it is. See, it has a position and a size. And actually, you can if you're scrolling here, you can also describe that in terms of radius, I think.
And then you just add the color.
Yeah.
Okay.
Right, and that's another property. There are other properties too. Actually,
Are those the ones you have to fill in?
you could have nothing.
Okay.
If you put nothing, it puts it at the origin with a radius of 1, I think.
Okay.
If you don't put any color, it makes it white. You can also give it a texture. Let's make it stucco. STUCCO. I think this will work. Texture, equals textures dot stucco. And no. Oh, wait, maybe it did work. But it's too small to see.
Yeah.
It's stucco. Trust me. Okay. But you don't have to put the material. Okay, I want this to be a vector location. Let's put this at 0.005, negative 0.010. So it's just a variable. It doesn't display anything there. So now I need to calculate, if I want to calculate the electric field here, I need the vector from the charge to the observation location. So I'll call that R, and I'll say equals what? Anyone have an idea? What would that equal?
The location of the sphere minus the location of the RO.
It'd be the other way around.
Oh, yeah.
Right. It's fun. So it'd be RO minus the location of the sphere is ball.pos. Because once I have POS in there, I can access that. That is the location of it. Okay. So now I have everything I need to calculate E. So I can say E equals K times Q times R hat, right? And R hat is a built-in function. Norm of R is R hat divided by the magnitude of R squared. Now I'm going to print E.
Oh, you already found Q.
Yeah, I already did fine. So there's the value of my electric field right there. Okay, but I want to now display that as a vector. Okay, so now I'm going to say E arrow equals arrow. The position of that arrow should be what? RO. I want it to start at the observation location. The axis should be what? E. Because I want the length and the direction of that arrow to represent the electric field. And what color should it be? Yellow is correct. Electric fields are yellow. That's a joke. You can make it whatever color you want. Okay. Now, that's not good, right? Because you can't see the ball or anything. So here you see a problem in that this ball and this position are actual positions. And I want to draw an electric field with actual distances. So if I'm going to make this, if you run it, it's going to have a length of 350,000 meters. That's the problem. Okay? And that's why you can't see anything. This is just a ginormous arrow, and it zoomed out so you can see the whole thing. So I need to scale this. So let's put up here scale equals scale factor. Let's say it's 300,000 times too big. It's actually 100 times bigger than that. So let's say 1 divided by 3 times 10 to the 5th, 7th, I think. 1 divided by 1 times 10 to the 7th. Or just 1 times 10 to the negative 7th. Okay. 1
million, right? So
and then over here, instead of just plotting E, I'm going to plot scale factor times E. Let's see what it looks like now. It's still too big. Let's make it 8. There. Now we can see the sphere. And actually, I want to make it a little bit smaller. Let's make that. What if I make it 9? It might be too small. I don't like that. That's okay. Okay. Because if I get too close, now let's just draw another electric field. RO2 equals vector. Let's say 0.005. 0.05 and 0.010, and then I'm just going to do the same thing over. I'll call this E2. Call that, I got to calculate a new R. R2 equals RO2 minus ball.pos. This is R2, R2, E2.
Magnitude.
So you guys don't need me. Now I have two electric field vectors. And you can see that one's closer and it's bigger. Okay. So, but there you see the things that we're going to use. We're going to use arrows and point charges. And this is how you would calculate the electric field due to a point charge. I could add in another point charge. I could make a dipole. I could do all that stuff. But that's not what we want to do. So I'm going to make another, I'm going to delete all this stuff. But are there any questions before I do? Because this isn't a numerical calculation. Because I didn't break anything into little steps. No questions. There are no questions because
E goes to other side.
you want E to go to the other side?
No, like it goes towards positive.
Well, it points away from the positive charge. Any other questions? I just deleted the whole thing. Okay. So now let's just go ahead and draw our rod, which we don't even have to do. You don't have to draw these things. I mean, the calculation is what we want, not the drawing. But so I'm going to say, what?
So the visuals always.
Yeah, it does help. So if I want that rod just like that, I need, first of all, I need to know the total charge on it. I'm going to call that Q. Let's just leave it at 1 times 10 to the negative 6 because who cares, right? And then how long would it be? Let's say it's like that big, 10 centimeters. Is that okay? So 0.1. So now what shape would we make a rod? A cylinder. And you want to make it a box? You can make it a box. Box work too. It doesn't really matter. I don't remember a cylinder. A cylinder is just like an arrow. So I need to give a position of, I want to put it at the origin. So I'm going to say the position is, I'm going to have it in the y direction. The position is going to be 0, negative L over 2, 0. Because that will put the, I need to indicate where the bottom of it is. Now the axis is going to be vector, oh, I didn't put vector over there. It's just going to be vector 0, L, 0. And the color, let's make it red again. And I didn't define the radius. It made a radius of 1. So let's see what. Axis size, I think it's do radius. Okay. So let's say how radius equals, if it's a length L, let's make the radius a tenth of L. What do you think about that? Let's make it a little skinnier. Let's make it 0.05. Okay, that's good. Do you like that? Mm-hmm. It's all shiny and everything. We don't need to make it out of stucco, do we? Well, we'll change that later. You need a what? You can make it matte. Let's see. Let's see, matte. What does it be called? Plastic. Let's see if we do plastic. I think that might work. No.
It's not material. It was
Textures?
texture.
I thought they're materials too. Okay, but obviously I don't know what I'm doing. Okay, we'll just delete that. We'll figure that out later. Okay, so now what I want to do, I need to do a couple things. I need to say N equals, and this is the number of pieces I'm going to break the rod into. Let's just start with 10. I'm going to break it into 10 pieces. And I need to find the observation location. I need to place where I'm going to calculate the electric field. RO equals vector. Let's see that it's 0.1 long, so let's say 0.08, 0.080. I'm making up stuff. Okay. Now I need to, let's go ahead and calculate dq. dq is the charge of each individual piece I break it into. So what would dq be in this case? Q divided by n, right? And this is better than saying, now, I want to do things generically. I want to do things in terms of n, so that if I change my number of pieces, nothing, all I'll do is change the number of pieces and everything else just works. Okay, now I need to break, this is the tricky part, okay? A numerical calculation, we normally think of some type of loop. We don't have to do that. We can cheat. Okay, what I'm going to do is break this into 10 pieces. I'll need 10 y values for the locations of those 10 pieces. So I'm going to say this. I'm going to use capital Y to represent a list of y's. And I'm going to say y equals a range from negative L over 2 to L over 2. And I need how many pieces? I need n. Okay, that's only 10 pieces. This made a, let me show you this. Print y. Okay, and let's just run this. Oops. A range from negative n, 10 pieces. Oh, that's a step size. I'm sorry, that's right. This is a step size. So I want to go from negative L over 2 to L. So let's call this dy equals, how big would each piece be? Yes, but what should I write? L over n. And then so down here in the range, I'm going to go from negative L over 2 to L over 2 with step sizes dy. And now I'm going to print dy. Print y. Okay, so you see down here, it printed out my 10 values of y. It goes from negative L over 2 to L. And these are actually, it's not quite even, but these are things that don't matter when you get the step size get smaller and smaller and smaller. It doesn't matter whether I'm in the middle of that piece or at the bottom of the piece. In fact, I'm at the bottom of the piece. But I don't care, okay? You could adjust this to make it in the middle, but if I have 10,000 piece sizes, the middle is the bottom. You see? Or if you squint, the middle is the bottom. Okay. So, but see, this is this is actually an array of numbers. It's a whole bunch of numbers, okay? And so that is my numerical part. Instead of doing a loop, I made an array. Does that make sense? But the key here is to remember this, a range function. Okay, so now I actually do need a loop. I made the pieces, but I need to go through each piece and calculate the electric field. So here's a trick. For y in y, watch this. I'm going to get rid of that. This is a loop that says go through every item in this array, capital Y, and call it little y. Print y. See, it did the same thing. It went through each piece and it printed it out, but now it's not an array, it's an individual number. Okay. Stop me if this gets boring or confusing. So, just like I said up here, I need to calculate, first I need RP. I need the vector location of that piece. So I'm going to say RP equals vector what? Anyone have an idea what RP would be? What's the last one? 0. Okay. So why is this first one right here, why is that 0?
Because we are looking for that, section of that.
Right, we have a vertical rod, and every one of those pieces has an x-coordinate of 0. They're all the same. It's all 0. And the same thing for the z direction. They're all 0. Okay? And so now let's just do this. Just for fun. Print RP. See, now I have all these, I have a list of vectors. I mean, I printed out the vector location of that piece.
I do have a question.
Yeah,
Why
great.
is one of them like 3, whatever,
Yeah.
to the negative,
It-
negative 8?
Because that's almost 0.
Okay.
Yeah. So what happens is it breaks. It's essentially a rounding error.
Yeah.
The way it's calculating those is by dividing this thing. It doesn't divide in evenly, so you get a rounding error. But it's not going to be a big deal. It's almost
basically-
0.
Yeah, it's basically
Right.
0.
Okay, so I have RP. So now I can calculate. Let's say this: DE equals vector 0, 0, 0. This is my electric field. I'm sorry. This is E. What I'm going to do is go through each piece, calculate the electric field due to that piece, and add it to the existing electric field. So I'm going to keep adding them up, but I need to start with something to add to. So I'm starting with the no electric field, and then each time I calculate an electric field, I'm going to add it to that. Okay, so let's say R equals what? Just like we said up there, we said R0 minus RP. Now I'm going to calculate D electric field. It's going to be K times DQ times what? Norm R divided by mag R. Now in Python, squared is not the hat 2, it's star 2. No clue why, it just is. Okay. Now I've calculated the electric field due to each individual piece. Now I'm going to say E equals E plus DE. So remember, this says take the value of electric field 0, 0, 0. Add this to it and make it the new value of the electric field. Okay. So let's just do this. Print E. And so now it's going to go through and print E. They should be getting bigger and bigger and bigger, and it's in reverse order. So you see it started off here, and it just keeps getting bigger and bigger and bigger, which is what we expected. Okay. That and this last one should be the total electric field. Okay, now let's make it, I'm going to make an arrow for that. E arrow equals arrow. I need a scale factor. Let's use that same scale factor. See if it works. Position equals RO. Axis, oops, it's RO. Axis equals scale factor times E. Color equals color.yellow. Okay. Can't see it. Okay, let's make it bigger. There it is. Make it a little bit bigger. That's pretty awesome, right?
I thought it was, is that one printing the last one?
That's the total electric field. Yeah, those printouts were the cumulative sums.
Okay.
Yeah. So what do you think about that? I'm impressed with myself. Okay.
And then you can move the point and it'll...
Yeah, I could change the point. This is, but how about this? How do we? This is the most important question. How do I know that what I did isn't completely bogus and is partially good, right? I mean, how do I validate what I've done? I mean, I got a pretty picture. I can partially validate it by looking at this, right? I know it should be, if this is a positive rod, it should be pointing away. But is it right? I mean, what do I do? How do I know that that's right? How do I do that? Maybe it's wrong. Maybe it's just a video game and it's just all make-believe and it's like the Matrix, right?
Pinch yourself, see if you wake up.
Oh, let's pinch myself and see if I wake up. When you did this problem in Physics 222, what did you do? How did you say, oh, it's correct, or it's not correct? You remember? Well, you checked the units, probably.
Yeah.
One of the things you did was just to see, as you get really, 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 really far away from it, what should you get? It should get close to what? Or it should go to 0. But also in this case, if you're far enough away from it, it should also look like the electric field due to what? A point charge. Okay. So let's try that. Let's first try putting this really far away. Let's put this at 5, right? Because that's, and let's print the electric field because we're not going to be able to see anything. So that's pretty, 5 meters away. That's infinity away, right? So it went down to 348 from like 300,000. So it got smaller. What if I did this? E point equals K times Q times, let's say, mag. Let's just get the scalar value. No. Let's get the real value. Okay, times norm RO divided by mag RO squared. That's the, if I assume all of the charge is I use Q, not dq, so this is the equation for the electric field due to a point charge. And now let's print E point.
Almost the same.
Isn't that amazing? I mean, come on.
Pretty cool.
That's pretty cool. Now now maybe it's bogus to begin with, so let's go back over here and change it back to the original location. They're not the same now, right?
Yeah.
Okay. So it does approach the electric field due to point charge. Really, you could do all sorts of cool things with this. You could plot the electric field as a function of distance from the rod, both for a point charge, which you know how to calculate, and for the rod. Or what about this? I do know the expression for the electric field due to a rod if I'm in the middle. You can analytically calculate that with calculus, right? So let's do that. So let's just move my position to the, right here, 0. Oh, that's not one, I'm sorry. Wrong 0, exactly. This one to 0. The y is 0. Which you can actually calculate the other one too. And I can look up the formula for the electric field due to a rod and see if these agree. And they're not going to. Because look, I have 10 pieces. What if I break this into 100 pieces? Okay. What if I break this into 1,000 pieces? Okay. And what happens to that expression as you go closer and closer? In fact, I've already done this. Let's see. Here's some graphs of some of the things that you could do. Here's more details of what we actually did. This is what it would look like if you put a whole bunch of arrows all over the place. Okay. This is, if you go in the center, then the green arrow is the green line is the exact solution that you would get from calculus. I'm not sure what the approximation is. The numerical calculation is right there, but it's right there along with. Oh, the approximation is if you assume it's an infinitely long. You have two equations for the electric field due to a rod. One of them is infinitely long and one of it's not. So there's three solutions here. The numerical is very close to the exact solution. This is the electric field as a function of, at one location, as a function of the number of pieces. Okay, so if I start off here with just 50 pieces, it's not a bad approximation, right? The exact answer is 7,000. I'm at like 6,900. It's pretty close. But then, as you can see, as I break this into more and more pieces, it gets closer and closer and closer to the theoretical answer. Okay.
Why is it jumping back down?
I don't know. I think it's either one of two things. It's either the difference between even and odd number of pieces in the thing. If you have an odd number of pieces, then you're going to have a charge in the middle. If you have an even number of pieces, you don't. I don't know that that's it. It could be that, or it could be a rounding error. Sometimes when it rounds.
Also, are you using the bottom or the middle of the piece? Because if you're using
Yeah.
the bottom, it would make sense.
That's
If you're
true,
using
too.
the middle,
It could be that too.
much.
Yeah, I don't remember what I did. And this is something that you can't do analytically. This is the electric field along a diagonal to that rod. Okay. And then this is comparing to a point charge, and you can see that it does approach. So there's a whole bunch of things you can do. Now, in order to do fun stuff like this, making graphs, you need to do something different. How would you make a graph of the electric field as a function of distance from the rod from this program? There's two ways to do it, but you don't think of what's the best way to do it. Think of how could you do it. If I want to plot the calculated electric field versus the theoretical electric field as a function of distance from the center.
You can put a variable on the location of RO, and then have it say it goes from range from here to
Okay.
here, and then plot.
So make the computer do it. Yeah, that'd work. What could you do this? Could you get a piece of paper and write down the distance, and then have it print out the electric field and write down the electric field, change the distance, have it print out the new electric field and write that down? Could you do that? Well, if you're only doing 20 points, it's not that bad. But the important thing is that's something that you know how to do. You don't have to say, I don't know how to make functions in GlowScript, and I'm confused, so I can't do it. You can do it. You don't have to do things the best computer way. I don't. Okay? You do it your way. If sometimes it's not the most optimal, big deal. That's not a big deal. Okay? Okay. So, if you look on Moodle, I put a whole bunch of documents for things for you to work on. I'm not sure what you want to do right now. I'm going to stop this recording, though.